This is my Lab 4 report on oscillations. The purpose of this lab was to analyze and model the motion of a spring mass system oscillating in 2 dimensions. I used Tracker to extract motion data from the video Spring Mass 2D MP4 and created a computational model in GoScript to simulate the motion and check if the energy principle holds true. In summary, my simulation closely matched the experimental data and the total energy of the system stayed nearly constant, meaning that the energy principle was satisfied. The system is controlled by 2 main forces: gravitational force, which is given by mgy hat, negative mgy hat, and the spring force, which is given by negative ks times s times l hat, where s is the stretch from the relaxed spring length L minus L naught. Using the momentum principle, F net equals change in momentum over time. I updated velocity and position over small time steps. Energy terms used in the model were kinetic energy, gravitational potential energy, spring potential energy, and the total energy was all 3 added together, and it should stay constant if energy is conserved. I completed option 1, which used the provided video. In Tracker, I calibrated the video with the meter stick and exported X and Y position data as headerless CSV file. In GoScript, I imported that data and simulated the spring mass motion using these constants provided below. Initial position and velocity came from the first 2 data points, and here's the code that I used for those 2. And then the simulation updated motion and recalculated energy every time step. In the animation, the blue ball shows the model prediction and the red ball shows the experimental data. They clearly overlap closely. This code calculates the ball kinetic, gravitational, and spring potential energies, then sums them up to give the total mechanical energy of the system. This section updates the motion of the ball using Newton's second law. It calculates gravitational and spring forces, finds the net force, updates the ball's velocity and position, refreshes the spring shape, and then computes the changes in kinetic, gravitational, spring, and total energies at each time step. This shows the modeled motion, blue, and the experimental motion, red, of the spring mass system over time. It illustrates how the mass both oscillates vertically and swings horizontally, forming a 2D path that the simulation accurately reproduces from the tracker data. This graph shows the change in energy versus time for the spring mass system. The plot compares kinetic energy, blue, which is kinetic energy fluctuations, the change in gravitational potential energy, which is red, and then the spring potential energy changes in green, and orange, which is the total energy of the system. The near flat orange line indicates that the total mechanical energy remains nearly constant, confirming that energy is conserved and only transfers between kinetic, gravitational, and spring potential forms throughout the motion. Let's start with what does it mean. When I plotted the kinetic, gravitational, and spring potential energies, they constantly change, but the total energy remained nearly constant. That means energy is conserved in the system. The small fluctuations are due to air resistance and measurement error, but overall this confirms the energy principle works for our model. The X and Y position graphs both show periodic motion with nearly identical periods, about 0.9 seconds and 0.92 seconds. That means that the horizontal and vertical oscillations are synchronized and that the model accurately describes real-world behavior. Now for the what-if reflection. What if the spring constant were larger? If Ks increased, the restoring force would be stronger, causing faster oscillations in a shorter period. In other words, the mass would move back and forth more quickly because the spring pulls it toward equilibrium more forcefully. By testing that in my code, the simulation indeed oscillates faster, confirming the prediction. In conclusion, the momentum and energy principles accurately describe the 2D spring mass motion. The energy principle was confirmed because the total energy remained constant. The periods in X and Y were nearly identical, showing good agreement with the experiment. And my what-if analysis demonstrates that the changing Ks, or spring constant, predictably alters the oscillation frequency. Together, these results show that my computational model and tracker data align closely, with only minor deviations caused by the friction and measurement uncertainty.